Okay, good afternoon, everyone. Thank you for showing up. Thank you for being here as always. I hope you're all having a good week. I did start the recording, so at this point, if you want to type your name into the chat so that we can have your record for the attendance, that would be great, and we'll make sure that you get your data in the next weeks. So good. I wanted to try. So one announcement, which I'll announce again at the end, is that the timing for next week has to change a little bit. So the timing for next week is going to be, and I know this is probably not as good a time, but it's unfortunately the only time I can do it next week. We have to meet next week at 2:30 instead of our usual time of 4:30, and I know that's not as good a time. But unfortunately, I have a commitment at 4:30, so 2:30 is the only time that we can do. Yes, Marcus.
Yeah, okay, thank you.
Okay, so I'll mention it again at the end of class, but just wanted to let you know now. Okay, so let's go back. Okay, great. Okay, so if you remember last time, we spent a lot of time talking about these trigonometric identities. And so we've built up this large arsenal of identities, which I've summarized for us over here on this page. So this is not every trigonometric identity, but this is maybe a good list of the most important ones. And so remember, it starts from these very basic ones. So these are what I'll maybe call basic identities here. So the most basic, most important identity in trigonometry is, sine squared x plus cosine squared x is equal to 1. Here I'm using the letter x. Here I'm using the letters a and b. There's not so much of a difference. It's just often you could write these as x and y if you wanted to. There's no difference there. So then you have here this set of 6 identities for cosine, sine, and tangent. These are the addition and subtraction formulas. And then over here, these next two are what are called the double angle formulas. And then last over here, we have what are called the half angle formulas.
All you want to ask.
Okay. And so there is one for tangent also, which I didn't write down, but I could only put as much as we could fit on the page. All right. So okay, so these are, there are more trig identities, and there's even one that we're going to talk about in the homework. But for now, these are the most basic ones that we're going to need. And so the homework questions the homework ones will deal with some more identities. And then today we're going to move away from trig identities, and we're going to talk about triangles again, like actual triangles. This is trigonometry. In the end, it should be related to triangles. Okay, so we'll go talk about that. All right, any questions on this? Okay, good. So let's go talk about the homework questions. Let's go back and do the homework questions. So we have here, the first one is just a standard question: calculate tangent of 7 pi over 12. So there's lots of different ways to do this. We're going to need to use either the addition formulas or the subtraction formulas, and there's lots of different ways to get this to work. So does anybody have, one way to try to evaluate this? And if you want to, you can convert it to degrees first. And if you want to just do it in radians the entire time, that's okay also. Yeah, Princeton?
Yes.
Yeah, Princeton?
Yes. We can change that 7 pi over 12 to a degree by multiplying by 180 degree over pi.
Yeah.
So we multiply the 7 by 180 degree, will give 1260. And then you divide by 12.
Yeah.
Now it will give you 105 degrees.
Great. So, sorry, over 12. Great, because the pi's cancel each other out. And so this becomes 105 degrees. Great. Okay, excellent. So this is the same as 105 degrees. So how should we do this? We could use an addition formula or a subtraction formula.
We
105
look
degrees.
for we do addition.
Addition formula over here. Okay, good. So what should we take for A and what should we take for B? If we want to do 105 degrees, we want to write it in terms of angles we know, right? So what should we take for our A value and what should we take for our B value in order to get 105 degrees here?
Yeah.
Yes?
AB equal to 60 degree.
Yep.
And BB equal to 45 degree.
Great. Okay. Yeah, that's exactly right. So we'll do, so, we know that tangent of A plus B equals tangent of A plus tangent of B divided by 1 minus tangent of A tangent of B. Okay, and so if we let A equals 60 degrees and B equals 45 degrees, then we have tangent of 105 degrees is tangent of 60 degrees plus 45 degrees. And that becomes tangent 60 degrees plus tangent of 45 degrees divided by 1 minus tangent of 60 degrees, tangent of 45 degrees. Okay. And so remember, what is the tangent of 60 degrees? So these are the good ones to have memorized, right? 30, 45, and 60. Remember tangent of 60 degrees? Yep. Yes. Yeah. So what's tangent of 60 degrees?
Tan of 60 degree will be root 3.
Square root of 3. Great. Exactly. So square root of 3 and tangent of 45 degrees is?
It's 1.
Exactly. Right. So square root of 3 plus 1 divided by 1 minus square root of 3 times 1. And so this is equal to square root of 3 plus 1 over 1 minus square root of 3. And if we want to simplify this, we can do that. We can multiply it by the conjugate. So we can multiply it by 1 plus root 3 over 1 plus root 3. And this turns out to be, when you multiply this all out, you have the 1 times the 1 is going to be 1. The square root of 3 times the square root of 3 is going to be 3. And then you have 1 times square root of 3, but you have to do that twice. So plus 2 square root of 3. And then over here, we have 1 plus root 3 times 1 minus root 3. That's going to give you 1 minus 3. Okay. So if you simplify this, you have 4 plus 2 root 3 over minus 2, which is going to give you, pull out the minus sign, and we'll divide by 2. So that's going to be 2 plus square root of 3. Okay. So this is the answer. This is tangent of 7 pi over 12. Okay. And it's good to just check that this is a negative number, right? 105 degrees is in the second quadrant, right? So we know that tangent is negative in the second quadrant. So it's at least a good check on our answer that we should have a negative answer. And that is exactly what we have here. We have a negative answer. Okay. So this is relatively straightforward application of the addition formulas. And then you have to do a little bit of rewriting in order to get it in the most simplified form. Okay, any questions about this example? It's okay. let's go to the next example. So homework example 2, derive a formula for sine of 3 theta, similarly to how we derive the formula for cosine of 3 theta. And we want to verify our formula for theta equals pi over 6. Okay? So if you remember, when we did cosine of 3 theta, we did cosine of 2 theta plus theta, and we used the addition formula. So for sine, we'll do something similar, right? So sine of 3 theta is the same thing as sine of 2 theta plus theta. And so what is the formula that we have for this? So we have to use sine of a plus b, right, instead of cosine of a plus b. So remember the formula for sine of a plus b? Well, we can look it up, right? So sine of a plus b here is sine a cosine b plus cosine a sine b, right? So we'll have to plug in that formula to write it down. So this is sine of 2 theta cosine theta plus cosine of 2 theta sine of theta. And now sine of 2 theta, we have a formula for that also. We have essentially, here it's written in terms of a, but sine of 2 theta is 2 sine theta cosine theta. Cosine of 2 theta has these 3 different formulas, and you'll get a slightly different looking formula depending on which one you use. All of them are going to be correct. They might just look a little bit different. So here, let's use sine a equals 2 sine a cosine a. So that's going to give us, so here we have sine of 2 theta is going to be 2 sine theta cosine theta. That's going to be this whole thing, right? And then still another cosine theta, right? That's what's here in green. And now on the other side, we have cosine of 2 theta. So, I mean, I don't really care which identity you use. Maybe we'll just use 1 minus 2 sine squared theta. That's one of the identities for cosine 2 theta is 1 minus 2 sine squared theta. And then we can say that whole thing times sine theta. Okay, and that's over here. So the color coding is just showing how I simplified things, right? And so if we want to simplify this a little more, this is 2 sine theta cosine squared theta. And then we have plus, well, here's a sine theta, and then minus 2 sine cubed theta. Okay, so actually probably, you know what? This is not as clean as I'd rather get a cleaner formula. So let me actually go back a step. Instead of using 1 minus 2 sine squared theta, instead of that, I'm going to use the other one just because it'll lead us to get a little more cancellation. I'm going to use 2 cosine squared theta minus 1 instead. The way I did it before is not wrong. It just won't simplify as easily. So I'm going to do it in a way that it simplifies a little bit more. So instead, so 2 cosine squared theta minus 1 is also one of the valid formulas for cosine of 2 theta. Okay, so if we write this down, this is 2 sine of theta cosine squared theta, and then plus, here I have 2 cosine squared theta sine theta, and then minus sine theta. Okay, and so what we are left with here when we combine these terms is 4 sine theta cosine squared theta, and then minus sine theta. Okay, so this is what we should get. So this is one of many valid formulas for sine of 3 theta. Okay, and if you want to, you could really get it all in terms of sine by converting this cosine squared into 1 minus sine squared, but I don't think we need to do that. You know, this should be good enough. Okay, so now we want to check the formula. So the question says to verify it for theta equals pi over 6. Okay, so let's try that. So for theta equals pi over 6, otherwise known as 30 degrees, right? So let's verify this. What do we have? We have sine of 3 theta is sine of 90 degrees. and that should be 1. And over here, if we plug in theta equals 30 degrees, what do we have? We have 4 times sine of 30 degrees times cosine squared of 30 degrees minus sine of 30 degrees. Okay, so, well, sine of 30 degrees is 1/2. So that's 4 times 1/2. And then cosine 30, right, is square root of 3 over 2. And we have to square that because it's cosine squared. And then minus sine 30, which is 1/2. And so let's see what this simplifies to. This is 4 times 1/2 is 2. Square root of 3 over 2 squared is 3/4, right? And then we subtract 1/2. And that's going to be equal to, well, 2 times 3/4 is 3/2 minus 1/2. And in the end, we get 1, exactly as we want. Okay? So these are equal. Okay. So as we see, at least when you plug in theta equals 30 degrees, this comes out to be right. You plug it into sine of 3 theta, you just get 1. And then you plug it into this formula that we got for sine of 3 theta, and we also get 1. Okay? So I wouldn't recommend memorizing this formula. I haven't memorized it. It's not so easy to memorize, but it is good to memorize the formulas for the double angle formulas, for sine of 2 theta and for cosine of 2 theta. Okay, those show up enough that they're worth memorizing. Okay.
Yeah.
Yep.
Brother
Questions?
Obi?
Yes, Princeton.
Yeah, I have a doubt somewhere where we have 2 sin theta for square theta plus 2 for square theta sin theta. I don't know. How come we got the 4 sin theta? Because the 2 that is the subscript for, let me say, the quotient for cos square and sin square, sin theta, rather.
Right.
But I don't know, there is a 2 that we brought together to make it to this 4.
So we have this term sine theta cosine squared theta, and this term is cosine squared theta sine theta. So they're written in different orders, but they're actually the same term, right? Sine theta cosine squared theta is the same as cosine squared theta sine theta. So we really have 2 times this, and then another 2 times the same thing. And so that gives us 4 times sine theta cosine squared theta.
Yeah.
Is that okay? Is that the question?
Yeah.
Okay.
Yeah, capital something there. They are the same, and
Exactly. Yeah. So the formula is difficult to memorize, and I would not recommend memorizing it, as James says. Don't memorize it. But it's good to know that you could rederive it if you needed to. Okay. It's not worth memorizing. Okay. Other questions about this one? Okay, good. So this is sine 3 theta, and remember, we did cosine of 3 theta last time, and I've already forgotten the formula there. The point is that you can rederive it if you want to by using this method. Okay? So, all right. So exercise 3. Can we use the formulas on page 5 of the handout? So that was page 5 of the last handout. Sorry, Harrison has a question. So any other concept to this problem? I mean, the concept, which I kind of talked about last time, is that you can get formulas for any multiple that you want. Once you have this formula, if you want to know sine of 4 theta, you could do sine of 3 theta plus theta and use the addition formula and again get sine of 4 theta. And you can get sine of 5 theta by doing sine of 4 theta plus theta. So once you have the formula for sine of n theta for any number n, you can always get sine of n plus 1 theta. So in theory, you could make sine of 10 theta, although it would be a very complicated formula and it would be hard to do. If you had enough time, you could do it. Okay. All right, so homework 3. Can we use the formulas on page 5 of the handout to derive a formula for cosine A times cosine B? Okay, and we'll verify our formula for A equals 30 degrees and B equals 60 degrees. Okay, so page 5, I guess this is page 5 right here. So let's say that we wanted to take all of these formulas that we have, and we wanted to get a formula for cosine A times cosine B. So does anybody see how we could use, maybe combine two of the formulas on this page to get something for cosine A, cosine B?
Yeah.
Yes, Clinton.
Yeah, we could take the identity for cosine of A minus B and cosine of A plus B and add both of them.
Exactly. Right? So that's perfect. So let's see what happens there. Right? So we're going to add these two identities. So I'm just going to rewrite them here. Cosine of A minus B equals cosine of A cosine B plus sine A sine B. And then cosine of A plus B equals cosine A cosine B minus sine A sine B. Okay? And so as Clinton said, we're going to add these, right? So let's add up these two equalities. So Clinton, so what do we get?
So basically, we have cosine of A minus B plus cosine of A plus B equals 2 cosine of A cosine of B.
Exactly. Okay, and so we want cosine of A cosine B, we just divide by 2, right? So we get cosine of A minus B plus cosine of A plus B divided by 2 is equal to cosine A cosine B. Okay, so this is another formula that you can get for what you get when you multiply a cosine of A and a cosine B together. This is sometimes called the multiplication formula. Okay. So very good. So does anybody have any questions on how we did this? You just have to take these two identities and adding them together is going to isolate the cosine A cosine B. And so then we can get this identity from that. Okay, so let's see what happens. Let's just verify this again. So if we have A equals 30 degrees and B equals 60 degrees, so the left-hand side is what? It's cosine of, well, 30 minus 60, right? So it's cosine of negative 30. So cosine of minus 30 degrees plus cosine of 30 plus 60. So that's cosine of 90 degrees divided by 2. Now, cosine, remember, is an even function. So cosine of 30 minus 30 is the same as cosine of 30, right? It's the reference angle. So cosine of 30 is square root of 3 over 2. Cosine of 90 degrees is 0. And then we divide that by 2. And so this becomes square root of 3 over 4. Okay, so that's the left-hand side. And then the right-hand side is just cosine A cosine B, right? So it's just cosine 30 degrees, cosine 60 degrees. Cosine 30 degrees is square root of 3 over 2. Cosine of 60 degrees is 1/2. And again, that's equal to square root of 3 over 4. Right. So we've verified the identity for these two angles. Okay. So again, probably not one that you need to memorize, but good to know that you can derive this. And just like we did it for cosine A cosine B, you can also do it similarly for sine A sine B. You just have to subtract these instead of adding these, right? If we subtract, the cosines will cancel out and we'll be left with 2 sine A sine B if we subtract the bottom one from the top. And then if you want to do sine A times cosine B, or cosine A times sine B, you can do the same thing just with sines instead of cosines. Okay, if you use the sine identities, then that'll get you similar formulas for sine A cosine B and cosine A sine B. Okay. Okay, so any questions on this? Okay, great. Okay, so let's move on to what we're going to do today. So the law of cosines. So we're going to talk about the law of cosines and the law of sines today. Okay, so here's the main question that motivates everything. Basically, if you have a triangle and you know some sides and some angles of the triangle, on many occasions, that's good enough to be able to solve the entire triangle, meaning you can figure out all the sides and all of the angles of the triangle. So the law of cosines is used in this specific situation. Let's say that we have the lengths A and B of two sides of a triangle, and you also know the angle C between them. And the question is, how can we figure out the third side, length C? So let me draw a picture. So if the angle is a right angle, then the picture looks like this. We have two sides A and B, and then we have the corner over here is the angle C. Maybe I'll label these AB, and then little c is the side that's opposite the angle C. And then, well, if the angle is a right angle, we can use the Pythagorean theorem, right? We know that a squared plus b squared is equal to c squared. And in other words, if we want to solve for c, this gives us that c is equal to the square root of a squared plus b squared, right? So this is fine. Okay, so maybe just for consistency, let me just rewrite this in reverse. So I'll call that c squared equals a squared plus b squared. Okay. All right, so for a right triangle, we know how to do this, right? Pythagorean theorem says if I know this side and I know this side, then how do I get the hypotenuse? I add up the squares and then I take the square root. But if we don't have a right triangle, we can still figure it out as long as we know what this angle is, okay? And the formula that we use for that involves the angle itself, and it's just a little bit more complicated, and it's what's called the law of cosines. So if you look at this over here, this part here is just the Pythagorean theorem. Right? C squared equals a squared plus b squared. But if your angle is not a right angle, then you have an extra term here. Extra term here for C. And something to note is that, well, if C is 90 degrees, then cosine of C is 0, right? Cosine of 90 degrees is 0. So, and what happens when cosine of C is 0? Then this term disappears, and you're left exactly with the Pythagorean theorem. So in that case, cosine of C is 0, and you have the Pythagorean theorem. Okay. So you should think of the law of cosines as a generalization of the Pythagorean theorem. It's like the version of the Pythagorean theorem that works even when your triangle is not a right triangle, right? It works no matter what that angle is between sides A and sides B. Okay. Okay, good. Any questions about, I mean, I'm going to prove it, but before I prove it, any questions about what this theorem is saying? So this, let me just draw a picture. This would be, for instance, if I had a triangle that looked like this. This is A, B, C, and these are angles A, B, and C. This is my angle C. Then the side C is not going to be a squared plus b squared, but I'm going to have to subtract off a 2ab cosine C. And you see that when this angle is acute, that makes sense because the side C is kind of shorter than it would be if this were a right angle. Like if I rotated B to make this a right angle, then the side C would end up being a little bit longer. Okay, but since it's an acute angle, the side C is going to be a little shorter. That's what's accounted for by subtracting off this term here. Okay, so, all right, let's do the proof of the law of cosines. So the law of cosines proof is really not that difficult. Okay, there's lots of different ways to prove it, but I'm going to prove it in a way. Sorry, was there a question?
Yeah, Prince.
Yes, Prince. Yeah.
Yeah, this one here from maybe like you're not getting. Yeah. What we have a c squared equals a squared plus b squared minus 2ab plus c. That'll be for any reason if we don't have, I believe that we don't have c value is so making the c to stay as c squared equal to all of this. If for any reason we don't have a, can any other formula be derived from this one Like for instance, we don't have a square. Can it be derived at the C from the Pythagorean theorem?
Yeah, I mean, right. So you can, I mean, do you mean like why do we have a formula for c squared but not for a squared or for b squared?
Yeah. Well, get C squared equal to A squared plus B squared minus 2AC cos C. Can another one be given from out of this where you don't have the value of A?
Yeah, I mean, so no, I mean you need to know two sides and an angle in order to get the third side. So you need all of this input. You need both the A and the B and the angle capital C. So yeah, you need the full information in order to get c squared. So sorry, I'm not getting you so clear.
So you can get it,
Yeah.
you can get it clear.
Yeah.
Suppose angle A was not given. What formula can you use?
Okay. Well, angle A is not given. We only know angle C. So little a and little b are side lengths, and angle C is an angle. Angle A and B are not given to you. You don't need them.
Oh, okay.
Yeah. It's only the side length A, the side length B, and the angle between them. That's all that's given to you. Right. So we're using capital letters for angles and lowercase letters for sides. Okay. Sorry, there's a lot of background noise, so it's hard to get you. Yeah.
Yes.
Yes, Princeton. Yes.
I don't know why Prince is asking, I don't know, asking a question like if A is angle A is given and then angle B and C is not given. I don't know the question like asking is this the question.
Oh, I see. So if you just know I'm saying so. Okay, so if you just know side A and side B and angle A, can you figure out side C? That's the question.
I think that's the point.
Okay, that's good. The answer is no, you can't, because what you're given there is what's called side angle, and side angle in general is not enough to figure out the other parts of a triangle. So it needs to be the angle in between the two sides. It needs to be the specific angle. If you're just given A or just given B, then that's not good enough, and you won't have a formula.
Okay, and again,
yeah.
Why in case if two angles are being given, like angle A and angle B is given?
Oh, that's different. You use the law of sines. So we'll talk about that after the law of cosines. Yeah. So for that, use the law of sines. Okay. This is the law of cosines. Okay. So yeah, no, in that case, you would use the law of sines. Okay. So let's see what happens here. Okay. So there's many different proofs of this law of cosines. And for us, we're going to be to draw the triangle in the following way. So I'm going to draw it on the coordinate axes. Okay, and I'm going to draw one point of the triangle at 0, 0. This is going to be angle C. I'm going to draw the side A lying along the x-axis. So this is going to be the point A, 0. And this is going to be a triangle with side A. And then I'm just going to draw the triangle above the x-axis. So it's going to look like this. Okay. So this is going to be side A. And this is going to be, corner A, and this is going to be corner B. And so this is side B, and this is side C. Okay. And now here's the key. The key is I want to know what the length of side C is, right? Well, I already know one point. Side C is a line between these 2 points A and B, right? I already know one of the points is A, 0. So if I know this point, then I can use the distance formula to figure out the side. And so how can I learn that point? Well, a lot of what you do in trigonometry and in geometry in general is you draw a useful line. So what I'm going to do here is draw the altitude from point A down to the x-axis. Okay, so I'll label my axes. It's good practice, x and y. Okay. And so, for instance, if I call, let's say I call this over here x. Actually, maybe if I call this u and I call this v, then this point A is at u, v. But if this is this angle here is angle C, well, then I can use right triangle trigonometry. So by right triangle trigonometry, So by right triangle trig, what do I know? I know that the cosine of C is equal to the adjacent over the hypotenuse. That's u over b. And sine of C is equal to v over b, right? Because it's the opposite side over the hypotenuse. I'm applying right triangle trig to this triangle over here that I drew with the altitude. Okay, so that says that u is equal to b cosine of C and v is equal to b sine of C. Okay. Okay, so great. All right, so u is b cosine C and v is b sine of C. And so that means this point here, we can write as b cosine of C and b sine of C. Okay, so what we get is that the side C is equal to the distance from the point b cosine C, b sine of C, to the point a comma 0. Okay, so all that we have to do is figure out this distance. And it turns out that this distance is going to give us exactly the formula in the law of cosines. Okay, so we'll do that. But just to recap, what I do is I draw the triangle like this so that the point C is at the origin and the side A lies along the x-axis. And then I draw this perpendicular line that allows us to get an expression for the point A in terms of coordinates. Okay, so this point A is b cosine C and b sine C. Okay, and once we know that, we know this has to be a comma 0 because it's just a distance a along the x-axis. And so now all we have to do is figure out the distance between these 2 points. Okay, is it clear?
Yes, okay.
Okay, great. Okay, so so C is equal to the square root of, well, we have b cosine C minus a squared, and then plus b sine C minus 0 squared. Or I can square both sides. I have that C squared is equal to b cosine C minus a squared plus b sine C squared, right? Minus 0 goes away. Okay, so let me rewrite this formula on the next page. I'll do another page. So recall we have C squared equals b cosine C minus a squared plus b sine C squared. Let me expand this out. So that's b squared cosine squared C plus a squared, and then minus 2ab cosine C. That's what happens when I expand out that square. And then b sine C squared is just b squared sine squared C. Okay. But if we rewrite this, I have a b squared cosine squared C and a b squared sine squared C. So that's going to simplify. So we have b squared, and I have the b squared gets multiplied by cosine squared C and sine squared C, right? So it's b squared times cosine squared C plus sine squared C. And then plus a squared minus 2ab cosine C. And now this, remember, cosine squared C plus sine squared C, the most fundamental identity in trig, that's just equal to 1. Right, so this just gives us b squared plus a squared minus 2ab cosine C, which is exactly the law of cosines. Okay, let me just switch these. So a squared plus b squared minus 2ab cosine C. Uppercase C. Okay. Okay, so this is it. This is the law of cosines, okay? You just have to draw the triangle, and then you draw one particular altitude, and then you use coordinates to figure out the distance. Okay. All right, so any questions about this derivation here? Okay, great. So this is the law of cosines. Okay, so c squared equals a squared plus b squared minus 2ab cosine c, right? Okay, so let's do an example. So suppose two sides of a triangle have length 5 and 5, and the angle between them is 60 degrees. So write it like this, 5, 5, and 60 degrees. What is the length of the third side? We'll call this c, right? Now, you can do this without the law of cosines. Does anybody see a quick, easy answer, easy way to do this without the law of cosines? If we know that you have two equal sides and a 60-degree angle between them, what kind of triangle does this have to be?
Yes,
Yes. Princeton?
this will be equilateral triangle.
Exactly. Do you know why? Why does it have to be equilateral?
Yes,
Yep.
because if you're using the Pythagorean theorem, it says that the sum of the length is equal to the longest side, which is the hypotenuse. And
Right.
if you square 5 and 5, it is 25, and the first
Okay,
code for the 25 will be 5. And the longest
right.
side will be equal to also.
Okay, let's be a little careful. You can't use the Pythagorean theorem here because it's not a right-angled triangle. Okay, if this is a right-angled triangle, this would be 5 times square root of 2. Yeah, Clinton? Or Abraham?
Yeah.
Clinton, yeah.
I think the reason why that triangle is an equilateral triangle is because since the angle between the two legs, 5 and 5 is 60 degrees, that means that the two base angle will be the same or they will be equal.
Right. So the point is we know it's isosceles because it has two sides that are equal, right? So we know in an isosceles triangle, the angles opposite the equal sides have to be equal. So if these angles are equal, and what do they have to add up to?
180.
Right, so all the angles add up to 180, and this one is 60, so these two angles have to add up to 120.
120.
Right, and so if they're equal and they add up to 120, the only possibility is that they're all 60 degrees. And once we know that all the angles are 60 degrees, then we know that all of the sides have to be the same also. Okay, so in this case, C is just going to be equal to 5. So you could use this geometric reasoning and get the answer, right? You just know that all of the angles have to be 60 degrees because these sides are equal, which means these angles are equal. And you can get that C is equal to 5. But let's say you didn't figure that out, okay? Let's say you didn't know that. The point is, you can also just use the law of cosines, right?
Yeah.
And the law of cosines is going to say that C squared equals, well, in this case, we have 5 squared plus 5 squared minus, remember what this is, C squared equals A squared plus B squared minus 2AB cosine C. So minus 2, and now A and B are both 5, so 2 times 5 times 5 times cosine of 60 degrees. And that's 25 plus 25. Well, 2 times 5 is 50, so minus 50 times cosine of 60 degrees is 1/2. And so that's just 50 minus 25, right? 50 times 1/2 is 25. These 25 plus 25 gives you 50. 50 minus 1/2 gives you 25. And that tells us that that's equal to 25. And so C squared equals 25. So since C squared equals 25, we have that C is equal to 5. Okay. Okay, since C squared is equal to 25, C is equal to 5. Okay. So there we go. So if you can do this nice kind of slick derivation based on isosceles triangles having equal angles, then that's great. You get the answer 5 easily. But what's nice about the law of cosines is that you don't really have to know that. You can just apply the formula, and you also get that C is equal to 5 by using the law of cosines formula. Okay? So either way, you get that the third side is 5. Okay, any questions about this? Okay.
I see it's okay.
Okay, good. Okay. So, by the way, maybe before I go on to the law of sines, let me just make a remark here. One thing that so maybe I'll do this on a new page. So, so remember that the law of cosine says c squared equals a squared plus b squared minus 2ab cosine c. Well, if c is acute, then what this tells us, then cosine c is greater than 0. So c squared is going to be less than a squared plus b squared, right? Because it's going to be a squared plus b squared minus something positive. On the other hand, if c is obtuse, it's bigger than 90 degrees, then cosine c is less than 0. So in this case, the cosine law is going to tell us that c squared is greater than a squared plus b squared, right? Because it's going to be a squared plus b squared minus something negative. So we're going to be adding it. If it's a scalene triangle, that's fine. So Armstrong's question, it's fine. You just use the formula. And it doesn't, there's nowhere in the formula that a and b have to be equal to each other. Okay, if a and b are different, you just use the formula and you get your answer. So if c is obtuse, then cosine c is less than 0. So c squared is greater than a squared plus b squared. And so what's the picture here? Well, right, if you have an acute angle, if this is A and this is B and this is an acute angle, here is C, definitely, smaller than if, if angle C were right? But over here, if we have some highly obtuse angle like this, so again, we have angle C here. If this is A and this is B and this is C, then we have that C here is going to be bigger than if angle C were right. Right, you can kind of picture, imagine you have A and B kind of lying on a hinge, and we want to know how long is side C. Well, the smaller the angle is, that means the distance between these two ends is going to be very small. So if you have a very acute angle, then C is going to be small. Little c is going to be small. If you have a big obtuse angle, then these things get very far away from each other. And that means that, side C is going to be very large. And so this is exactly what the cosine law is telling us. It's telling us that if you have an acute angle, the distance, the length of side C is smaller than what you would expect from a right triangle. And if you have an obtuse angle, then the length of side C is bigger than what you would expect from a right triangle. Okay. Okay. Good. Any questions on this? Okay. So, all right, great. So let's look at the law of sines, okay? So this is a different situation than the law of cosines. So let's say instead we're given two angles of a triangle and the length of the side between the angles. So how can we figure out the lengths of the other two sides? And so again, if one of the angles is a right angle, then you can do this with right angle trigonometry, right? So if we're given this angle, let's say again we have C, A, and B, let's say that we know this angle theta, and then we're also given this side here. So if this would be A and this would be C. So, for a right triangle, if we're given, let's say, theta and also B, then we can figure out the other sides because, for instance, that sine of theta is equal to, well, let me do cosine first. Oh, no, yeah, no, sine of theta, that's fine. So sine of theta is equal to A over C. Oh, so let's look at cosine theta first. Given theta and B, then cosine of theta is equal to, cosine of theta in this case is equal to B over C. So C equals B cosine theta. And what else do we have? Well, so once you know C, so then you can get A from the Pythagorean theorem if you want to. Which is, in this case, is going to look like A squared equals C squared minus B squared. Okay, so if you have a right triangle, then you can, and if you're given the right angle and some other angle and also the side in between them, then you can get the other sides by using this right triangle trigonometry. Okay, so you can get C from using cosine, and then you can get A from the Pythagorean theorem. But in general, if you just have a normal triangle, then you use what's called the law of sines. And the law of sines says that A over sine A equals B over sine B equals C over sine C. So the ratio of the length of a side to the sine of the angle opposite that side is always the same, no matter which side you choose. And in fact, this quantity, earlier on, we talked about circumscribing a circle around the polygon. So this quantity is actually equal to 2 times the radius of the circumscribed circle. Okay, we won't really talk about that too much, but there is an actual quantity that these are all equal to. Okay, so just like the law of cosines, I'm going to prove the law of sines, which is not very hard. It's easier than the cosine law. And then we'll do an example and show how this works to solve a triangle. Okay, the law of sine says A over sine A equals B over sine B equals C over sine C. Okay, so how do we prove this law of sines? And there's also lots and lots of different proofs, but let me do one where we're just going to draw a picture. For this one, we don't really need coordinate axes. So let's say this is A, this is B, and this is C. So what I'm going to do is, again, just draw this altitude from C. So we have sides here. This is B, this is A, this is C. So we're going to draw, again, an altitude from point C, vertex C, down to the side C. Okay? And then I'm going to call this X. Okay? And so what I'm going to do is I'm just going to write down 2 expressions for X. So by the way, that's a right angle. This is a right angle also. So 2 expressions for X, one using each small triangle. So the first expression says what? Well, if I look at this, I have angle A over here. So if I want to relate X and B using angle A, well, I have that the sine of angle A, that's the opposite over the hypotenuse. So that's going to be X over B. Or in other words, X is equal to B sine of A. Right, just from this triangle over here. So this is, from the left triangle. Right, sine of A is equal to X over B, so X is equal to B sine A. I use this triangle. I have my angle A. X is the opposite, B is the hypotenuse. Now I use the right triangle, and I look at the sine of B. Well, that's the opposite over the hypotenuse, right? So sine of B is equal to X over A, or X equals A sine B, right? This comes from the right triangle, in which I don't mean it is a right triangle, but I mean the triangle on the right. Okay, so this is the left triangle, this is the right triangle. Okay, but both of these are equal to X, which means they have to be equal to each other, right? So since both B sine A and A sine B equal X, they have to be equal to each other. So we have that B sine A is equal to A sine B. And then we can divide both sides by sine A over sine B. And so this gives us that, so we can divide by sine A sine B. And that's, if we divide the equation by sine A sine B, we exactly get that B over sine B equals A over sine A. okay? And that gives us just one of the identities, but you can just repeat this argument for any pair of sides. Okay. So this is why. So this proof, I think, is maybe even simpler than the cosine law, right? You just draw the altitude, and then you just get two different expressions for right. You just get two different expressions for the length of the altitude. One is in terms of angle A on the side B, and the other is in terms of angle B on the side A. They're just kind of symmetric expressions, and setting them equal to each other, you get this sine law. Okay. All right, so any questions about how this is derived?
Yeah, yes, sir.
Yes, okay.
Rich, yeah.
Question? Yeah.
I want to know as to whether the triangle inserted here, it has angle, and then what the position of the angle before, because I'm looking at the opposite or the adjacent to be placed different way. So where is the angle facing?
So here, I mean, this here is angle A, and this here is angle B, right? So I'm using for this x, it's always going to be the opposite side. That's why we have sines, right? So this A here, we have the sine of A is x over B, and the sine of B is x over A. So in both cases, it's the opposite side to the angle that we're looking at.
It's on this.
Right, sine of A
Okay.
is the opposite over the hypotenuse, so x over B. And sine of B is x over A, opposite over the hypotenuse.
It's very honestly, I'm just sorry.
Okay, is that good?
Yeah, it's okay.
Okay, great. Okay, so this is the proof. So let's use this now. So what's an example? So suppose one side of a triangle has length 6, and the angles adjacent to that side are length pi over 3 and pi over 4. What are the lengths of the other two sides? So let's draw. Usually I like to just draw. I'll draw my 6 at the bottom. So I have a pi over 3 over here. Maybe that's the pi over 4. And then maybe this is pi over 3. So I have pi over 4, and I have pi over 3. Let me call these sides maybe A and B. And so we want to solve for A and B, right? And so maybe it's good to have this in terms of degrees. So this is 60 degrees. This is 45 degrees. So the first thing that you do when you have one of these law of sines problems, when you have to find the other sides, is you first figure out the third angle, right? That's very easy to figure out the third angle because, so first find the third angle. Well, that's pretty easy, right? We just have 180 degrees equals 45 degrees plus 60 degrees plus theta, where this is this third angle, right? And so if you solve for this, you're going to end up getting theta equals 75 degrees. Okay, so this is 75 degrees, or if you want it in terms of radians, that's going to be equal to 5 pi over 12. Okay, so here we could write 5 pi over 12 if we want. Okay. And so then second, so you can always figure out the third angle because you're given two of them. So the second one is use the law of sines. Okay. And so what do we have for the law of sines? The point is every side over the sine of its opposite angle is the same as the one of these things that we know. So we know one of these ratios, that's 6 over sine 5 pi over 12. We won't use the addition formulas here. We're just going to use a calculator to make the computation a little easier. But what we have here is that the law of sines tells us that A divided by sine of pi over 3 is equal to B divided by sine of pi over 4. And that's equal to 6 divided by sine of 5 pi over 12. Okay? And so now we can use each of these equations to solve for a, right? So to solve for a, this gives us that a, well, a over sine pi over 3 equals 6 over sine 5 pi over 12. So I can just multiply by sine pi over 3, right? So a is equal to 6 times sine pi over 3 divided by sine 5 pi over 12, which is the same as 6 times square root of 3 over 2 divided by sine 5 pi over 12, which is the same as 3 square root of 3 divided by sine 5 pi over 12. And so this I'll just use a calculator for. So 3 times square root of 3 divided by sine of 75 degrees. Okay, so this looks like it gives me about 5.38. That'll be side A. Okay, and then side B is going to be same thing, except we have b over sine pi over 4 equals 6 over sine 5 pi over 12. So the sine pi over 4 has to move up here. So we end up getting, so b is equal to exact same expression, but we use sine pi over 4 instead. Sine pi over 4 over sine 5 pi over 12. Pi over 12. And that's, so sine pi over 4 is 45 degrees. So that's root 2 over 2. So 6 root 2 over 2 divided by sine 5 pi over 12. And that's equal to 3 square root of 2 over sine 5 pi over 12. And then this is roughly equal to about 4.39. Okay. So these are the answers that we get over here, 5.38 and 4.39. Right? And but they both come from this law of sines equation. The point is we have three different quantities. One involves one of your unknown sides. The other one involves the other one of your unknown sides. And the third one is completely known because, excuse me, because you're given the side. So the third one is completely known. You're given the side. And even if you're not given the opposite angle, you can always figure it out. Because once you know two angles of a triangle, in fact, once you know any two angles of a triangle, you can always figure out the third one. So if you know two angles of your triangle, you can figure out the third one. And then you have, what you need in order to do the law of sines. Okay, and in this case, we have a scalene triangle, right? The sides are length 6, 4.39, and 5.38. Okay. Okay. So this is how you can figure out the other two sides using this law of sines. All right, any questions? Okay, great. Okay, so the last thing I want to do is just show you there's some nice computer animations that you can use to see these things. So the GVSU, this is a college in the United States called Grand Valley State University. So if you look at this, he has these very nice applets that illustrate the law of sines and the law of cosines. So what I'm going to do is I'm going to share my screen with you and show you these. So let's look at this. Where are we? Okay. So let me go to following websites. So http gvsu.edu/s/01b. So this illustrates the law of sines. And it's based in GeoGebra. So what you can do is you can use a mouse and you have a triangle here. And what it'll tell you, it tells you what is the angles, they call the angles alpha, beta, and gamma. So it has the angle measures here, and it has the lengths of the sides, A, B, and C. And then it calculates the ratio, sine of alpha over A, sine of beta over B, and sine of gamma over C by the law of sines. these all have to be equal to each other, and they are. It's 0.148. And so what you can do is you can just draw, you can, do whatever you want to do. You can drag these points around, make whatever triangle you want. You can make basically a right-angled triangle if you want, or pretty close to a right-angled triangle. And it'll calculate your A, B, and C, but it'll always show you what these ratios are. And the key thing is watch how these ratios over here change. Notice that they're always changing in parallel, right? No matter what I draw over here, whatever I draw over here, these ratios always change at the same time. That's because the law of sines is correct. Okay, so all these ratios are always going to be the same, no matter what kind of triangle you draw. So you can fool around with this. That's kind of nice. And then something similar, you can do the same thing, but for the law of cosines. So same thing, but instead of O1b, you do O1c. So in this case, what do we have? We have, again, it keeps track of all the sides and all of the angles, and then it calculates c squared, which is this, and then a squared plus b squared, which is this, and then a squared plus b squared minus 2ab cosine gamma. Gamma is what they're using for c, which is this. And what we should see is that a squared plus b squared minus 2ab cosine gamma is always going to be the same thing as c squared. So again, if I move the triangle around, you can see the top that, this row and this row should always be the same, no matter how I move the triangle, right? So here, for instance, if I move this point, I'm not changing side C at all. I am changing a squared plus b squared because I'm stretching them. But whenever I stretch them, I'm also changing the angle between them. And so it turns out that this expression over here, the a squared plus b squared minus 2ab cosine gamma, is always the same, no matter how I move this point, right? It's always going to be 13.92 over here, as long as I'm leaving side C fixed. Okay, and you can see, for instance, if you do a right angle, if you make gamma a right angle, or you make it pretty close to a right angle, it's about as close to a right angle as I can get, then what you see is that the c squared is more or less the same as a squared plus b squared, right? It's only because this is not exactly a right angle. It's a little bit more than 90 degrees. But basically, these are the same. If I can make it an exact right angle, then all three things would be the same. Yeah, that's about as close as I can get. Yeah, can't really get any closer than that. Okay, yeah. Okay, so this is just like kind of fun, and so the address is in the notes if you wanna go and play with these triangles a little bit, but it teaches you how to do. It just shows all the important measures in the triangle, and it verifies that the sine law and the cosine law are both correct. Okay. So let me go back to my sheet. So give me 1 second. Okay, so Zoom. Okay, so let me share a screen. Okay. Good. So this should be, hold on, it's taking a little bit of time to catch up with me. The screen seems not to be on yet. Hold on. What's going on here? Are you getting my screen, or are you getting the homework, or no, you're still getting this menu screen, right? Hold on. What is going on here? Am I like not on the Wi-Fi somehow? What's going on with Zoom? Let's try this again. Let's try this again. Okay, there we are. Okay, good. Okay, so these sites, you'll be able to see the addresses on when I send out the notes, and so you can go play with these if you want. Okay. So homework exercises, I realize I want a third exercises. So the first one is 2 sides of a triangle have lengths 2 and 3, and the angle formed by those 2 sides is 30 degrees. Determine the other side of the triangle. So this is going to be a straightforward law of cosines. Number 2 is, does a triangle whose side lengths are 6, 8, and 9 have an obtuse angle? You can also use the law of cosines for this if you want, or you can use the law of sines. And then number 3, which I'm going to add here, says interpret, this is a bit more of an open-ended question, but interpret the law of cosines, when angle C is equal to 180 degrees. Okay, so interpret the law of cosines when angle C is equal to 180 degrees or 0 degrees, right? So in both of these cases, what does that mean? I mean, if angle C is equal to 180 degrees, then you kind of have this, right? This is C and this is A and this is B. It's like barely a triangle, right? This would be the 180 degrees. And if angle C is equal to 0 degrees, then what you have is C, and then this point is both A and B, right? A and B are so close together that the angle is 0 degrees. So the question is, can you figure out a way to make the law of cosines meaningful in these kind of edge cases, these extreme cases? Okay, so so that's the homework questions, and then a notification, which I mentioned at the beginning, but not everybody was there, is that next week, unfortunately, I have to meet at a different time because I'm busy at 4:30. So this is only for 1 week. Class is going to meet at 2:30 instead of at 4:30. I'll send out a reminder about this, and I know this is maybe not as good a time for everybody, so I apologize for that. But that will be, yeah, so class will meet at 2:30 next week, and then the week after we'll go back to the regular time. Okay, so I'll send out a reminder about that as the class gets closer. Okay, so thank you as always for your attention, and if there's any questions, you can ask them now. All right, so if there's no more questions, I'm gonna stop the recording.